The Orchestrated Objective Reduction, Orch OR model, represents a theoretical framework proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff in the mid-1990s to explain the origin of consciousness. This model integrates elements of quantum mechanics, molecular biology, neuroscience, and quantum gravity, positing that consciousness arises from quantum processes occurring within the brain, rather than solely from classical neural computation. At its core, Orch OR asserts that consciousness emerges from quantum computations performed in microtubules, cylindrical protein structures composed of tubulin dimers located inside neurons. These microtubules are proposed to serve as the substrate for quantum information processing, functioning far beyond the capabilities of conventional synaptic activity. The theory builds on two primary components: orchestrated quantum coherence. Biological processes within microtubules maintain coherent quantum superpositions, multiple states existing simultaneously over relevant timescales. These superpositions involve collective dipole oscillations or vibrational modes in tubulin proteins, enabling quantum computation analogous to qubits in a quantum computer. The orchestration refers to biological mechanisms, such as synaptic inputs, memory, and cellular architecture, that regulate and sustain these quantum states, preventing immediate environmental decoherence. Objective reduction, OR. Penrose's proposal addresses the measurement problem in quantum mechanics by suggesting that superpositions do not collapse randomly upon observation, but undergo objective reduction due to gravitational effects at the Planck scale. When the superposition reaches a critical threshold of space-time separation, related to gravitational self-energy, the wave function undergoes spontaneous, non-computable collapse. In Orch OR, this orchestrated collapse, hence Orch OR, produces discrete moments of conscious awareness, choice, or experience. Each collapse event selects one outcome from the superposition, yielding a unified, non-algorithmic conscious moment approximately every 25 milliseconds, corresponding to much over 40 Hz gamma synchrony in EEG readings. This mechanism addresses several long-standing issues in consciousness research. It accounts for the binding problem, how disparate neural activities unify into coherent experience, through non-local quantum coherence across microtubules. It provides a basis for non-computable aspects of cognition, e.g., insight, understanding, which Penrose argues classical computation cannot achieve. It links consciousness to fundamental physics, suggesting experiential qualities arise intrinsically from space-time geometry during OR events. Orch OR predicts that anesthetics disrupt consciousness by binding to microtubules and suppressing these quantum processes, a claim supported by some experimental observations of anesthetic effects on microtubule vibrations and energy migration. Recent developments, 2023 or 2025, have provided indirect empirical support, including evidence of quantum coherence and superradiance in tryptophan networks within microtubules at physiological temperatures, energy migration sensitive to anesthetics, and studies showing delayed anesthetic-induced unconsciousness in models with stabilized microtubules. Computational simulations and quantum biology findings, e.g. in photosynthesis and avian magnetoreception, have also bolstered plausibility for warm-temperature quantum effects in biology. Nevertheless, Orch OR remains controversial and lacks definitive experimental confirmation. Criticisms include rapid decoherence in the brain's warm, wet environment, as highlighted in early calculations by Max Tegmark, challenges in scaling quantum effects to neuronal timescales, and the absence of direct evidence for gravitationally induced collapse in biological systems. Mainstream neuroscience largely favors classical emergent explanations for consciousness, viewing quantum involvement as unnecessary or implausible at relevant scales. Ongoing research in quantum biology continues to test Orch OR's predictions, particularly regarding microtubule quantum vibrations, anesthetic mechanisms, and potential links to discrete perceptual cycles. While intriguing and increasingly discussed in interdisciplinary contexts, the model has not achieved broad acceptance and requires further rigorous falsification or validation,